Section: Introduction. In this section, we discuss the advancements in deep learning architectures and the technique of greedy layer-wise pre-training that has played a crucial role in training deep networks. Before 2006, training deep architectures was quite challenging, but the discovery of greedy layer-wise pre-training changed the game by allowing the training of general deep architectures in a stage-wise manner. This technique involves gradually adding new layers to a network and training them along with the existing layers until the desired depth is achieved. Although modern techniques like residual connections and normalization layers have made it easier to train deep networks without pre-training, the success of transformer-based architectures in tasks like language modeling has led to a trend of using larger models for better performance. However, training these giant transformer models can be time-consuming and expensive, prompting researchers to explore faster training methods. One effective strategy that has resurfaced is stacking initialization, where new layers are initialized by copying parameters from existing layers. This approach has been shown to speed up the training of deep transformer models significantly. Unlike traditional random initialization, stacking provides a clear advantage in terms of training efficiency. The concept of stacking in deep learning is reminiscent of boosting in machine learning, where classifiers are trained in a similar stage-wise manner. Both techniques involve initializing new components by copying parameters from existing ones. The recent theoretical explanation for the effectiveness of stacking in transformer models is based on the assumption that each transformer block is a good learner with limited examples. Our contribution in this work is a theoretical framework that explains how stacking accelerates the training process by enabling an accelerated form of gradient descent. We show that stacking initialization leads to faster convergence compared to zero or random initialization methods. Specifically, for boosting models with stacking initialization, the loss decreases at a rate of O(t)(-2), which is faster than the rates achieved with zero or random initialization. Furthermore, we demonstrate through experiments on synthetic and real-world data that our theoretical framework holds true and leads to improved convergence rates in practical scenarios. Section Summary. In this section, we delve into the historical significance of greedy layer-wise pre-training in training deep architectures, particularly in the context of deep learning revolutionizing machine learning. We explore the recent resurgence of greedy layer-wise pre-training in speeding up the training of large transformer models, drawing parallels with boosting algorithms and showcasing the theoretical underpinnings of the effectiveness of stacking initialization in accelerating stage-wise training procedures. Section: Related work. In this section, we explore the concept of boosting, which is a traditional method for creating additive ensembles through iterative training. Boosting has a rich history of research, and interested readers can refer to the literature for more information. Previous studies have investigated training deep residual networks layer by layer. Initially, researchers focused on adding trained layers to the model one by one while keeping the lower layers fixed. This was followed by fine-tuning the entire network. In recent years, progressive stacking has emerged as an effective way to train deep networks, especially transformer-based architectures. Researchers observed that neighboring layers in trained transformer models exhibit similar attention patterns. By transferring parameters from the previous layer, a better starting point for optimization is provided. Gradual stacking, based on the idea that trained transformer blocks are good at learning from few examples, has been shown to significantly speed up training time. We consider a general supervised learning scenario where examples are drawn from a distribution. Our goal is to predict outputs in a certain dimension using a loss function to measure prediction quality. Predictions are made by functions, and we assume these functions are integrable with respect to the distribution. The loss function is extended to predictor functions, and training aims to find a function that minimizes this loss. We analyze this in a functional setting, although in practice, functions are parameterized, e.g., by neural networks. We define an ensemble learning setup where we aim to approximate the best predictor using a sequence of functions. The ensemble consists of simple functions that are easy to optimize. A predictor function is derived from the ensemble by combining its constituent functions. The loss of an ensemble is defined based on this combination. We consider two aggregation operators: addition, which sums the outputs of the ensemble, and residual composition, which composes the functions in the ensemble. Section Summary. In this section, we explore the concept of boosting as a method for constructing additive ensembles through stage-wise training, with a rich history of research in this area. The idea of training deep residual networks layer by layer has been previously investigated, focusing on gradually adding trained layers to the model and fine-tuning the entire network. Recent advancements in progressive stacking have shown promise in training deep networks, particularly transformer-based architectures, by leveraging the similarity in attention patterns between neighboring layers to provide better initialization for optimization, leading to significant improvements in training efficiency. Section: Greedy Stage-Wise Training. In this section, we explore greedy stage-wise training, which is a simple method to train ensembles gradually. We start with a partial ensemble, f_1, f_2, L dots, f_t, and aim to add a new function f_t+1 that minimizes the loss of the updated ensemble. In practice, achieving this ideal scenario is challenging. Instead, we commonly use two strategies: initializing the new function thoughtfully and employing early stopping during optimization to keep the new function close to its initialization. To analyze these practical aspects conveniently, we represent them in a functional optimization framework. We begin by assuming that the new function f_t+1 starts at a carefully chosen value f_t+1, 0. We denote the ensemble containing f_1, f_2, L dots, f_t, f_t+1, 0, as f_t+1, 0, and a general ensemble as f. Early stopping can be viewed as a form of L_2 regularization, ensuring that the trained function f_t+1 remains close to its initialization f_t+1, 0. For theoretical analysis, we approximate the loss function L, f, by linearizing it around the initialization f_t+1, 0. This approximation involves the Frechet derivative and the inner product in L_2. By minimizing this approximation, we obtain f_t+1. In specific scenarios like additive and residual compositional models, minimizing the expression over f provides insights into obtaining f_t+1. We can then explore different initialization strategies such as zero initialization, random initialization, and stacking initialization in the context of these models to observe various forms of functional gradient descent. When functions are initialized as zero functions, stage-wise training leads to functional gradient descent with a specific step size. This concept is well known in the additive setting, where boosting resembles functional gradient descent. The result for the residual compositional setting seems to be novel. On the other hand, when functions are randomly initialized, stage-wise training results in stochastic functional gradient descent on a smooth loss function. This smoothing effect can be likened to convolving with a Gaussian. The update in this case can be interpreted as a stochastic functional gradient descent step on the smooth loss function. Section Summary. In this section, we explore the concept of greedy stage-wise training, a method used to progressively train ensembles by adding new functions to an existing ensemble. The process involves minimizing the loss of the new ensemble to obtain the next function, often initialized carefully and optimized using early stopping to keep it close to the initialization. By modeling these practical considerations in a functional optimization setting, we can analyze specific initialization strategies like zero, random, and stacking initialization, which lead to various forms of functional gradient descent in additive and residual compositional models. Section: Stage-wise training with stacking initialization recovers accelerated functional gradient descent. In this section, we explore stage-wise training with stacking initialization, which helps recover accelerated functional gradient descent. When functions are initialized in a stacking-like manner with f_t+1, O equals F underscore T, known as stacking initialization. The ensemble aggregation operator being addition leads to an updated ensemble predictor formula resembling Nesterov's accelerated gradient descent. This formula involves a constant beta in the range 0, 1 that can vary with T. By adjusting the stacking initialization to F underscore T plus 1, O equals beta F underscore T, we can precisely retrieve Nesterov's accelerated gradient descent, enabling accelerated descent for training additive models. When the ensemble aggregation operator is residual composition, stage-wise training with the stacking initialization F underscore T plus 1, O equals F underscore T results in an updated ensemble predictor formula that differs from Nesterov's update rule. The key distinction lies in the replacement of F underscore T, circ F underscore T1, by F underscore T, circ F underscore T. Although challenging to formally prove, we anticipate accelerated convergence in this scenario due to the proximity of iterates F underscore T1 to F underscore T as they approach the optimal function. This accelerated convergence intuition is further validated in certain deep linear networks, where stacking indeed facilitates an accelerated convergence rate. To demonstrate the provably accelerated convergence rate enabled by stacking, we focus on training deep residual linear networks devoid of nonlinear activations and residual connections. These networks, which compute linear functions through a parametrization involving weight matrices, are commonly studied in deep learning theory. Considering a supervised learning setup with inputs x in math_bb_r (d) and outputs y in math_bb_y, where the loss function L math_bb_r (d) times math_bb_y to math_bb_r is convex in the first argument, we assume the expected loss L W is L smooth and mu strongly convex in W. The deep residual neural networks under scrutiny consist of T layers with weight matrices W_1, W_2, L dots, W_T, computing a function x, maps to W_Tx where W_T equals I plus W_T, I plus W_T1, L dots, I plus W_1. The condition number, kappa of the loss is defined as kappa equals frac L mu. Section summary. In this section, we explore stage-wise training with stacking initialization, which leads to accelerated functional gradient descent resembling Nesterov's accelerated gradient descent. By modifying the stacking initialization, we can recover Nesterov's accelerated gradient descent for both additive and residual compositional models, enabling accelerated convergence rates during training. Specifically, in the context of deep linear networks without nonlinear activations, stacking demonstrates a provably accelerated convergence rate, showcasing its effectiveness in enhancing training efficiency. Section: Derivation of stacking updates. In this section, we derived stacking updates for training a deep residual linear network with beta scaling. To initialize the weight matrix of the T+1 TH layer, we set it to beta W_T, where beta is a constant between 0 and 1. By following the same steps as in the functional setting of the previous section, we obtained the formula for W_T+1. Even though stacking differs from Nesterov's method, we can prove that stacking still leads to accelerated convergence. If we initialize the first two layers close to the optimal values, the suboptimality gap after T stages of stacking is approximately express tilde omega T sqrt kappa. This rate is similar to Nesterov's acceleration, whereas stage-wise training with zero initialization would result in a larger suboptimality gap. The proof for the theorem showing the convergence rate is provided in the appendix. We demonstrate that the difference between the loss at W_T and the optimal W** is bounded by a term related to the initial distance between W_0 and W**, scaled by a factor of sqrt kappa, and exponential in T sqrt kappa. This bound holds under certain assumptions on the initial loss values L W_0 and L W_1. By setting the gradient step size and momentum parameter appropriately, we can express our linear networks as perturbed versions of Nesterov's acceleration. Through induction, we prove that the perturbation term and potential functions satisfy certain conditions, leading to the desired convergence rate. The final claim of the theorem is then obtained by simplifying the expressions and showing the exponential convergence rate as expected. Section Summary. In this section, we derive stacking updates for training deep residual linear networks with beta scaling initialization. Despite differences with Nesterov's method, stacking still achieves accelerated convergence rates, showing a suboptimality gap of express tilde omega t sqrt kappa after t stages, comparable to Nesterov's acceleration. The proof outlines that stacking can yield significant convergence improvements when the initial layers are close to optimal, showcasing its effectiveness in training deep linear networks. Section: Base Case. In this section, we will first demonstrate the base case. We show that for phi 1 and phi 0, they are both less than or equal to a value called delta. By utilizing the strong convexity property of a function L, we can set an upper limit on the initial potentials phi 0 and phi 1. Assuming certain conditions on L, W_0, and L, W_1, we can establish that phi 0 and phi 1 are indeed less than or equal to delta. Next, we move on to the inductive step. For a specific time point t within a range, we aim to prove two things. First, the difference between two vectors is bounded by a certain value, and second, phi t plus 1 is less than or equal to phi 0. By making use of the inductive hypothesis and strong convexity, we can derive relationships involving delta and other parameters. We introduce a new term eta_t to simplify the expressions and show that certain conditions hold for phi t and phi t1. Furthermore, we establish that W_t1 is invertible, and we can define delta_t accordingly. By bounding the perturbation norm using the inductive hypothesis and certain facts, we can show that delta_t is indeed less than or equal to a specific value, thus completing our inductive step. Moving on to proving a key fact, we utilize the inductive hypothesis to bound the singular values of a matrix. By invoking a well-known inequality, we can establish the invertibility of W_t1 and derive an upper bound on the Frobenius norm of W_t1, -1. This completes the proof of the fact. The theorem presented in this section discusses a local convergence result, assuming the network is initially close to the optimal solution W***. Additionally, a global convergence result can be obtained by incorporating a brief warm-up period before stacking layers. The corollary of the theorem provides further insights into the convergence behavior of the network. To support our claims, we recall the convergence rate of gradient descent and apply it to the training of deep linear networks. By combining these results, we can derive bounds on the difference between the network outputs and the optimal solution. Finally, by setting appropriate parameters, we can ensure that the network converges locally to the optimal solution. Section Summary. In this section, we establish the base case by showing that the initial potentials phi 0 and phi 1 are both bounded by delta, leveraging the strong convexity of L. Moving on to the inductive step, we aim to prove that left L vert delta_trite R vert lec alpha left L vert W_t, W_t1, right R vert and phi t plus 1, lec phi 0, by assuming certain conditions and utilizing the inductive hypothesis. Section: Key ingredient of proof. Robustness of Nesterov's accelerated gradient descent method. In this section, we delve into the key ingredient of our proof, the robustness of Nesterov's accelerated gradient descent method. The main idea behind theorem's result is that Nesterov's method can handle changes in its update rules quite well. This robustness is precisely defined in lemma. The lemma is presented in a general setting because it can be useful on its own. To prove this, we assume that the perturbation term's size is limited by a certain value. We introduce some coefficients. Tau equals frac 1 sqrt kappa plus 1. Gamma equals frac 1 sqrt kappa minus 1. And rho equals frac mu gamma 4 plus gamma equals frac mu 4 sqrt kappa. 3. Here, tau represents momentum, gamma is related to the convergence rate, and rho penalizes the presence of perturbations delta underscore t. We define iterates z underscore t equals frac 1 tau x underscore t. Frac 1 tau y underscore t for all t in the range t. It's important to note that the lemma's claim about y underscore t doesn't directly rely on delta. Therefore, we can set delta underscore t equals 0 to ensure delta underscore t lec alpha y underscore t y underscore t1. To prove the lemma, we need to show that a specific function phi is a potential function, meaning that for all t in t phi t1 lec 0. This claim leads to the conclusion that phi t lec phi 0, which directly implies the lemma's statement. We then focus on proving this claim by introducing a potential function phi and comparing it to the usual potential function used in Nesterov's acceleration, denoted as phi underscore orig. By bounding the difference between phi underscore orig t and phi underscore orig t1, we can show that phi t1 lec 0 even when considering the perturbation delta underscore t. This analysis is crucial for understanding the robustness of Nesterov's method in the presence of perturbations. Section Summary. In this section, we highlight the robustness of Nesterov's accelerated gradient descent method as a key element in the proof. The theorem's core insight lies in the method's ability to handle perturbations in its update rules, formalized in a lemma of independent interest. The lemma's general setting showcases the method's resilience to perturbations, crucial for its convergence properties. Section: Experiments. In this section, we empirically validate our theoretical findings. We focus on deep linear networks and squared losses. We use the same function class as in our theory, testing on synthetic data with square loss. The output space is y equals r caret d, and for a predictor x mapping to w underscore tx, we consider the loss function. We use a data distribution D where samples x, y are drawn as follows. X is sampled from n, 0, sigma, and given x, y is generated as y equals w caret asterisk x plus xi, where xi is a random variable with mean 0. The expected square loss can be explicitly written. For squared loss, the condition number of the expected loss depends on the covariance matrix, sigma, denoted as kappa equals frac sigma underscore text max sigma underscore text min sigma. For squared loss, we have closed form expressions for stacking updates and Nesterov's updates. The smoothness of the loss L depends on the largest singular value of sigma, i.e., L equals sigma underscore text max sigma. We compare the performance of 3 updates: vanilla gradient descent, stacking updates, and exact Nesterov updates. In stacking updates, only the last layer is updated at each stage. We consider points in D equals 20 dimensions, generating the ground truth W caret asterisk as I plus sigma S, where S is a random positive semi-definite matrix with spectral norm 1. We vary the condition number, kappa, observing that stacking updates outperform gradient descent for ill-conditioned data. When comparing stacking updates and Nesterov's updates, we notice differences as W caret asterisk moves away from identity. Stacking updates may benefit from an initialization closer to Nesterov's updates. We explore training all layers in each stacking stage, using different initialization schemes. Both stacking schemes outperform a random baseline, especially for ill-conditioned data. Section Summary. In this section, we empirically validate our theoretical results by conducting experiments on synthetic data using deep linear networks and squared losses. We consider the condition number of the expected loss, explore stacking updates and Nesterov's updates for squared loss cases, and compare their performance with vanilla gradient descent. The experiments show that for ill-conditioned data, stacking updates converge faster than gradient descent, and the behavior of stacking updates closely mirrors that of exact Nesterov's updates, suggesting potential improvements in initialization strategies for stacking stages. Section: Stacking for BERT base with parameters. In this section, we developed a theory that requires us to initialize at the t+1 th stage with f_t+1 (O equals beta f_t), where beta is a value between 0 and 1. The introduction of beta is important for achieving a faster convergence rate in Nesterov's method. However, the standard stacking initialization does not include the beta parameter. To ensure that adding the beta parameter does not negatively impact the effectiveness of stacking, we conducted experiments on BERT base. We introduced a trainable parameter, beta, which scales the output of the newly added transformer block in stacking. Initially, we set beta to 0.9 and 0.99, which are commonly used values for momentum parameters. Our findings, depicted in a figure, demonstrate that incorporating the beta parameter does not compromise the effectiveness of stacking. Additionally, the plot illustrates a slight improvement in the final log perplexity when using the trainable beta